recording. So today we're going to be working on something that I would have wish I had time to go over last week, but I didn't really feel like there's time. But I mean, honestly, this is a pretty good day. Did I go over goats and cars, or no? No? No, the Monte Hall problem? Okay, great. We're going to have lots of fun today. Okay. As I mentioned, we're also definitely going to be approximating pi. So again, we're going to be working on Monte Carlo approximations. Again, solving a statistical problem by just doing by doing randomly choosing a game rather than not. Again, I highly recommend watching these videos, looking at this article. We're going to go over, though, this, and you can see our textbook does have this section on Monte Carlo simulations, right? And it doesn't talk about how, like a lot of science these days, we do simulations in order to figure them out. How we simulate things rather than build real things in order to get good answers. This has 3 simulations. I'm going to do 2 of them, and I'm going to be doing them completely out of order. Rather than talking about approximating pi, which we've done with the Madhava-Leibniz formula, I'm going to scroll pretty far down to the Monte Hall challenge. Okay, so yeah, the video's out, no longer there. That's fine. But the Monte Hall problem is extremely famous in certain circles. Back in the 90s, there was a woman who ran or I think she still writes it. There's a Ask Marilyn there's an Ask Marilyn magazine column in Parade magazine. It's been running since '86 and became really famous when she got one question in the column, and it concerned a problem called the Monte Hall problem. Monte Hall problem is a brain teaser based off of a game show called Let's Make a Deal. Okay, it's been in a lot of countries, a lot of reproductions. Monte Hall served as the host, hence why it's called the Monte Hall problem. And it's a particular segment from the show where you're presented with 3 doors, okay? And you're presented with 3 doors, and the host tells you that behind one of these doors is a brand new car. And behind the other 2 doors is a goat. Now, I have to say this because my wife works at the Philadelphia Zoo, and she often works with the goats. So I have to say this. The goat is considered to be less desirable than the car. The car is what we are looking for, not the goat. We want to get the car in this problem. Okay? So, but behind one of these doors is a goat. Sorry, behind one of these doors is a car. Behind 2 of these doors is a goat. So, of course, we don't know which is which, but Monte does. The host does. So he basically says we're going to play a game. Choose one of the doors at random, and that's the door you're going to get. So we choose a door, such as door 1 or 2. Right? Let's just assume, for the sake of argument, we don't choose door C. Or door 3. I'm going to say choose door 1 over here. Okay? I'm going to choose door number 1. And before we reveal what we got, Monte goes over to one of the doors that we did not choose. This is the key here. He goes to a door that we did not choose, in this case 3, and he opens it to reveal that there's a goat. He's always going to go over to one of the other doors that we didn't choose and open it up and show me there's a goat there. And then he asks me, are you feeling lucky? Do you want to switch? Or do you want to stay on your initial guess? Right? So So the original problem, as specified, is suppose you're on a game show and you're given the choice of 3 doors. Behind one is doors of car, behind the other goats. You pick a door, say number 1, and a host who knows what's behind the doors opens another, say number 3, and then he says to you, and number 3 which has a goat. He then says to you, do you want to pick number 2? Is it advantageous to switch to your choice? So is it advantageous to switch your choice? And the crazy thing about this one is that we call this the Monte paradox because it breaks a lot of your logic unless you know about a lot of Bayesian statistics, which is a pain. So, anyone know the answer to this one? Yes. You want to switch. What's the chances if you switch? It's 2/3. Yeah. The answer is, believe it or not, you want to switch. Because if you switch, you have a 2/3 chance of winning. That doesn't seem to make a lot of sense because your brain goes, there's 2 doors. I switch, it's 50-50, right? But again, it's about those priors, okay? Now, if this does not make sense to you, don't worry, you are not alone. You are not alone by the far. Savant's response was the consistent should switch by standard assumptions. The switching strategy had a 2/3 probability of winning the car as opposed to choosing your initial one, which had a 1/3. Okay? Now, the probability does depend on the assumption, but many readers of Savant's column refused to believe that switching was beneficial and rejected our explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them calling Savant wrong. Even when giving explanations, simulations, and formal mathematical proofs, many people did not accept that switching was the best strategy. Paul Erdos, one of the most prolific mathematicians in history, remained unconvinced until he was shown a computer simulation demonstrating the predicted result. And when we say Paul Erdos was prolific, okay, just how actors have something called a Bacon number, which represents how far away they are from Kevin Bacon. If they've got a Bacon number of 1, they've acted with Kevin Bacon. If they've got a Bacon number of 2, they've acted with somebody who's acted with Kevin Bacon, or acted with somebody with a Bacon number of 1. Kevin Bacon himself has a Bacon number of 0. Mathematicians also have an Erdos number, which basically says how far away are you from publishing with Paul Erdos. Paul Erdos had a Erdos number of 0. Anybody who published with him had an Erdos number of 1. Anybody who published with somebody with an Erdos number of 1 has an Erdos number of 2. I have an Erdos number of 5, so I published with somebody with an Erdos number of 4, which was my advisor, who turns out had published with somebody with an Erdos number of 3. So, yeah. So, and why is that? Why do we use that? Because he published around 1,500 mathematical papers. Now, this is one of the 2 mathematical problems I find particularly interesting. The other one being the Collatz that involve him, the other being the Collatz conjecture, which is an unsolved problem with mathematics, which is that given any number, if it's even, divide by 2, if it's an odd, multiply by 3 and add 1. If you keep doing this sequence, right, because if you divide it, it's going to get halved. Eventually, halving it will make it an odd number. Odd numbers will doing this, multiplying by 3 and adding 1 to an odd number will turn that number into even, right? The question is, with enough repetition, does this result, do all positive integers go to 1? And that's still an unsolved problem in mathematics. And we have at least shown that it's held for all numbers from up to 2.36 times 10 to the 21st. But no actual proof, like mathematical generalized proof, has been found. We've shown that it probably works, but we haven't 100% proven it, right? And yeah, Pale Erdo said mathematics may not be ready for such problems, even though it's such a simple one, right? And we can see this graph going, showing, hey, if we started at 19, multiply it by 3, no, let's start with, what is it? For even numbers, divide by 2, multiply by 3, add 1. So let's see, where is this? These numbers don't seem right. Why is that? Directed orbits, that is not what I'm looking for. Where is that graph that I'm looking for? Here we go, trace of all numbers that have fewer than 30 steps. So if we start with, like, say, 320, you have that to 160, have that to 80, that gets half to 40, 20, 10, 5, multiplying by 5 by 3 and adding 1 gives you 16, which then goes to 8, 4, 2, and then 1. And then 1, once you get to 1, you're in a loop that resumes at 4. So most people basically would say this stops at 1. Okay, that's an interesting problem. Anyway, back to the Monte problem. So Monte problem, we've specified that switching is better. Even though it seems like, right, there's 2 doors now, it should be 50-50. Why are the chances the way they are? So first off, the assumption here is that when we choose a door, say door number 1, the host is always going to open a door that has a goat. And he can always do that because there's 2 goats. So if you choose a goat, he can always open the other goat. Okay? And then he's asking you if you can switch, because he never reveals the car, right? It's always the suspense is, that's not the way suspense works. The suspense is not very interesting if you're choosing between one goat and another goat. It's, are you getting the goat or the car, right? So he's always going to show you that goat. Now, and that changes kind of the logic of it, right? If you selected a goat to begin with, he's going to show you the other goat, right? If you selected a goat to begin with, he shows you the other goat. So now you're down to, you've been given some extra information that this other thing would have been a wrong choice. And so your initial choice, which you made when you didn't know anything, well, that would have had a 1/3 chance of being right, right? The other one now has a 2/3 chance of being right because we know the other one, we can't choose it anymore. It's been revealed. So that's why you switch. Because based off this new information, we now know that our initial 1/3 chance has, well, our initial chances were 1/3, 1/3, and 1/3. And now those chances, well, I made a choice. My chance of getting right on my first try are still 1/3. And now that he's revealed one, well, the chances of this has kind of moved over into here, that pool of possibilities. I find this becomes a bit more intuitive if we do this ad absurdum, which is to say that instead of doing 3 doors, I've got 1,000,000 doors with 1 car and 999,999 goats, okay? And so I'm going to choose door number 1 again, right? And now Monte Hall reveals 999,998 goats behind a bunch of doors, leaving only 2 left. And we know that behind one of those, behind either the door I initially chose and the door that's left, there's a car there. And the question is, how lucky do you think I am? That's kind of the ad absurdum of it, okay? Right? And we can also just think of it from just kind of the idea here. We're always going to assume we choose door number 1 because statistically that's just simply, it's always easiest if we assume we keep choosing the same door, right? If we start with a goat, he's going to show us a goat, and there's going to be a car, and then the doors behind car number 3. We switch over to 3, we win. If we chose a goat our first time and the car is behind door number 2, he's going to show us door number 3, in which case we switch, we win. If we choose a car initially, he's going to show us one of the 2 goats, we switch to the other one and we lose. So there were basically 3 possible configurations to this. And if we switch on two of them, we win. And if we stay on one of them, we win. Okay? There's a lot of different explanations here on this, right? A lot of different explanations. We can show by simulations, which this is what we're going to do. And I really like a lot of these puzzles and these kind of games like this. The other paradox that you should be aware of, especially if you're going into pre-law, is the Simpsons paradox, which has nothing to do with the franchise, the media franchise, The Simpsons, but has to do with the fact about statistics, and it often gets used in law. Basically, it says that that just because that individual statistics and combined statistics can be very, very different. A good example of this, classically, is batting averages, which is that a person can have a better batting average individually in individual years, but still have the lower batting average overall. Right here, Derek Jeter had the lower batting average in '95 and '96, but combining the aggregated result of over 2 years, he had the better batting average. Okay, it just had quirks like this. This can also happen with, like, again, with legal cases about gender bias, about all sorts of things. It is very, there's a lot of interesting paradoxes to know about. And the final bit of, I guess, instructor's privilege that I get to talk about today is my other kind of game, and this is less of a paradox, but more of an interesting question, which is the ultimatum game. Which gets into these kind of questions about the way people think and the way they behave, right? Which is which is basically you get two players, the proposer and the responder. Let's say that somebody on this side of the room is the proposer. It's your job to take $1,000 and give a single offer on how to split it with the responder, who's on this side of the room. Okay, so you're given $1,000. Your job is to decide how you're going to split the money. The responder's job is basically you either accept or reject it. It's a single offer, and if you accept it, you both get the money as proposed by the proposer. However, if you reject the money, neither of you get the money. Okay? Now, this may seem silly, okay? After all, a lot of you think, okay, proposer, 50-50 split. People are going to take a 50-50 split. That's fair. Take if you've taken a philosophy class and learned about utilitarianism, the idea here is that humans basically do things that take actions that benefit themselves, right? Well, wouldn't you just, and let's say the proposer says, let's split $1,000, $999 for me and $1 for you, right? Well, that's one more dollar than you had before, so why aren't you going to take the money? And we know why why the rejecter would reject the money. Because we're insulted. Because that's a great offense, right? Why in the world would you not do that? Because humans love punishing bad behavior. We just love it. It's something, it makes us feel really good to do that. We have found that, and so the question that people want to know from this game is, at what point do humans start to go, F off, I don't care how much money you've just, that represents, it's not a fair split, so I'm rejecting it, right? Okay, or does the amount of money matter and versus the percentage, right? So a lot of questions there. And we found, offers of less than 30% are often rejected. Basically, there's a 50-50 shot of anything less than 30% being rejected. Whereas basically, pretty much anytime you see 50-50 splits are pretty much accepted. Also, like another fun one was, what effect does the person being drunk have? Well, if the responder is drunk, turns out they'll reject anything that's pretty much not fair. So it's a very fun problem. So let's go back to Let's Make a Deal and our problem now, and actually do this. So Monte Hall. So we need to simulate this problem, and we kind of have learned how to do this. So let's go ahead and start by outlining this, okay? Before getting into, let's see. Let's go ahead and do Monte. Actually, wait, it's over here. So it's in Runestone, so I can just do. Why am I logged out of Runestone now? How weird. Okay. Yeah, that way I can share it with you. Okay. All right, so let's go ahead. So we're going to need to do this game not once, not twice, but a lot of times. And I often put that as the number of times I'm going to play a game as variables, right? And then I'm going to go ahead and create a function I'm going to call game. Return false. And the way I like to do these kind of games or these things is basically a game is going to return what I consider important about the game. Sometimes, in some simulations, that's the number of turns it took for the game to complete. That's one of the things we care about in the pig extra credit. In a lot of games, it's did I win or lose, right? Or was the result higher than some amount, right? A lot of the problems we're going to be looking at win or lose. So if it's a binary result, did I win, did I lose? I often like to do false is lose or didn't succeed, true is I won or I succeeded, okay? So right now, I'm just simply doing false because that allows me to simulate basically the entire thing without actually programming it in. And so the way this is going to work is very straightforward. I'm going to count the number of wins I have, and I'm going to say, hey, for blank in range trials, I'm going to say result is equal to, let's go ahead and I'm going to run this a bit in a few more lines than I normally do. So I'm going to play the game, get the result of the game, and I'm going to say, hey, if result of the game is what I'm looking for, if I won, then I'm going to say my wins increased. And then I'm going to say, and then to get the percentage, I'm going to say wins divided by the number of trials I had to do. Run. And of course, I won none of the time because I lose every time, right? Okay, if I put in true over here and assume I won every time, I'd be getting a 1.0. Let's go ahead and add some randomness in. Import, just to kind of show you, and import random, right? Return random. I can actually do this in one line. Random.rand. Don't copy this down. I'm going to delete it very quickly. Random 1, 2 equals 1. Basically, I'm saying choose between 1 and 2. If it's 1, return true. Then you'll see that gets very, very, very close to half, as you would expect, right? And then if there were 4 numbers to choose from, right, so I had a quarter of a chance succeeding, that's around 25%, as you can see. The more trials we run, the closer this gets to the actual value, okay? The actual expected value. But now let's actually simulate our actual game of goats and the like, okay? So let's go ahead. We are going to have so let's go ahead and I like to, again, generate our doors as, let's say we've got ourselves as a list. We've got ourselves I'm going to just use G for a goat. another G for another goat, and a C for a car. Hopefully that doesn't strain the incredulity of anybody. I could also just type it out, but that's fine. Okay, single letter is fine here. So we've got our doors. Now what I've got to do is I need to make sure that they're placed that Monte's going to place them randomly, right? So I can do that with a nice, easy function, random.shuffle. So anytime I'm so just remember this for the exam. Basically, you're going to be doing one of three possible things. Okay, random, a coin flip or a dice is one of the possibilities. If it's a coin flip or a dice, you're just generating a random number with rand_int, most likely. Okay, or you could do that with rand_int, right? 1 or 2 for a coin flip. And then for a dice, you just use rand_int in the range of that dice, typically 1 to 6, right? Most of the dice you're going to be working with are 1 to 6, right? The other possibility is a problem like this, or a problem of cards. And if it's a card problem, I'll already have the deck written out for you, so you don't have to write 2, 3, 4, 5, 6, king, jack, king, queen. So you don't have to write all that, right? But if you've got a deck of cards and you need to make it random, then you shuffle that deck of cards. So basically, you're going to be using one of two techniques on an exam to randomize stuff. You're going to either define what it is and shuffle it, or you're going to generate a random number. The fun part is you can go from either one to the other pretty easily. We could always just not shuffle the doors and then use a random integer to say, hey, where's the goat going to be, right, instead, right? Or in the case of generating, I'll get to you in a second. In the case of rolling a dice, you could create a list of all the numbers, shuffle it, and say the first one is is the roll. Yes.
Is there anything like that on the practice exams?
Yes, there are 2 problems like this on the practice exam they put on. So Penny's game specifically is the one I'm thinking of for that one, where you're flipping multiple coins. Okay. So we've got our doors. We've shuffled our doors. We have. We're going to basically go with our choice is going to be doors. The very first door, right? And now we can kind of work off of the logic. I'm going to say I'm going to basically write switch is equal to true, so we can test out the different strategies, right? So if switch is equal to true, then that means what? If we chose a door initially, it might have a car or goat. We don't know, but Monte does, and we of course would know just by looking and kind of doing that. So, but we know from our logic that basically if we initially chose, basically we know that if we decide to switch, the only way we're going to lose is if we initially chose the car, right? So if the door is equal to switch and our choice equals a car, return false. Else, return true. Okay, so we can now play this. And we got, as I was saying, around a 2/3 chance of winning. Because the only way we lose is that if we initially choose that car and then switch away from it. It's the only way we lose. Okay. Can I just simply switch this to false? What happens if I just switch this to false? No. Switch is equal to true and choice is equal to car. Yeah, that's always going to be false. That makes sense, why that would be. So let's go ahead and clean this up a bit. If switch is equal to this, if. Boop. And then else, over here, if switch is equal to false, if switch was equal to false, if our choice was a car, return true. We can actually probably clean up this logic easily, but I'm refusing to do so because I want to get to our next problem. Whoops. Return true. Line 8, expected. Yeah. Okay. There we go. So yeah, if we decide to not switch, we see our chances, the reciprocal 33% chance of winning. Share code. Okay. The second problem, which I'm going to skip over, is one that actually a lot of students end up doing, or something students end up doing. At least one student a semester does something like this for their final project, which is predicting the price of a stock based off of prior data. So that can be actually a very fun project if you want to take a look at that. There's lots of art. Because everybody wants to be the one to figure out how to make money, there's a lot of different strategies and different articles on how to do it. It's a lot of fun. Okay. Now let's talk about approximating pi once again. So you may remember from all the way back in the third week that we learned something called Madhava-Leibniz formula, which is this formula for approximating pi, which said that pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth, and so on and so forth, right? So we could do that, but it's not a very efficient formula. So we're going to learn another yet inefficient way to do it that's based off of geometry and turtles. We're going to use turtle to do this one. It's a bit more intuitive to understand than just doing this because we've just got this formula and it's got mathematical proofs. This one we can actually understand kind of why it's going to work. All right, so over here, we're going to assume we are throwing darts at a dartboard, okay? So the idea here is let's say we've got a dartboard, okay? And I actually do need to draw this out because when you think about a dartboard, you can throw stuff at a dartboard and it's going to either hit or miss, right? But does the miss mean I throw it and it ends up in the ceiling, right? Not in this case. We're going to be a bit more defined about what we've got here, okay? So I'm going to do some very quick, very easy drawing. We have a circle of sorts, right? That's our dartboard. And then we've got and I'm going to put it in a square of sorts. Where I was, here, you go here, and you go here. And now I stretch you out and make you look like I'm really good at drawing. Okay? So there's our square, and there's our circle. Okay? The circle is our dartboard. Okay? And our square is basically the range of possible space that our dart could end up in. So pretend we've got like a magic magnetic force field that's going to drag anything that goes way off course back into here, right? So if I throw a dart, it's not going to go into the audience or something, okay? It's going to end up somewhere in this square. It might end up inside the dartboard. It might end up outside the dartboard. Now, because now we're going to use numbers here, but because I am not very smart, I'm going to use small numbers, okay? We are going to use a unit circle, right? Very, very, very simple circle, right? We are going to say that this is a unit circle because that's easy, right? This dartboard is going to be a unit circle. What does that mean? It's just a boring circle with a radius of 1. That makes math very easy, right? Unit circle, radius 1. Okay? So if this unit circle is a radius of 1 and this is touching and the circle touches the edge of the square, right? Can anybody tell me what the side length of the square is? Not a trick question. It is what it appears to be. So how long is the side length of the square? Yeah, I saw somebody. Yeah, I see. Nobody's saying it, but they are throwing their fingers out. So yes, this entire side length is 2. Very easy math, like I said, okay? We also know that the diameter of this circle is also equal to 2, right? Because that's twice the radius. All right. So here's a bit of fun. Okay. If we define that center of the circle as 0, 0, right? We can define this kind of as then, if we define the center as 0, 0, then this on an xy plane, this would be 1, 1, and this would be, right, 1, -1, right? And this would be 1, 0, right? No surprises here. I'm just trying to show that's very unsurprising, right? If this was a graph, if we put this on a graph, right? Very unsurprising kind of there. This is what those would be. So what we're going to do is that we are going to generate, to throw a dart, what we'll do is we'll generate random x's and random y's. And what we do is that basically that to generate x and y, those will be generated by choosing a number in the range of -1 to 1, right? That's how that way they land in the legal space. We just generate a number between -1 and 1. That's how we throw it. We generate an x value that's between -1 and 1. We generate a y value that's almost certainly going to be different. Okay? Okay. And that will let us know basically where these, and so that will generate a place where the dart basically lands. The question is, obviously, if I'm looking at the screen, I can tell, oh, this point is inside the circle, but this point is outside the circle. So the question is, how can I do that mathematically? Now, this is not the math class and not geometry class, so you probably did not come with the formula prepared, but it is a very convenient formula. It's a distance formula. We can basically we can answer this by asking what is the distance from the center. Because we know that the way a circle works, it is defined by a radius. If it's inside the circle, it's inside the distance of the radius, right? So basically, if the dart is less than 1 from the center, it's inside the circle. And if it's more than 1, it's outside the circle. So distance from the center. And we've got a nice distance formula that works in multiple dimensions. In 2 dimensions, it looks like this, which is x squared plus y squared. And then take the square root of that. Okay? And that gets you the distance. Okay? Of that. From the center. Okay? And so we can use that formula to say, hey, where did something land? Now, here's why we care about this. Okay? We're going to do some of the easiest math we've done with. You've ever done. Okay? So this is why we care. The area of the circle of this particular circle is what? Well, what's the formula for an area of the circle, right? It is pi r squared. Okay? We've already defined this as the easiest possible circle we can do, right? Which is radius 1. So the radius of, so the area of the circle, is pi. On the flip side, we've got this square, right, which is a 2 by 2 square, right? And the area of this square is almost as easy to figure out, right? What's the area of this square? It's basically the side length squared, or for any rectangular thing, it's base times height, right? So it's 2 times 2. So the area of the circle compared to area of the square is pi to 4, right? And think about it. This takes up about pi square units of space versus the total amount of 4 squared units of space, right? It's taking up most of the space in here. So what we could do is we can say, hey, we're going to just keep throwing darts at this thing. And then as we throw more darts, we can count the number of things that land inside the circle to the total number of throws. And if we keep doing that enough, that's going to eventually get closer and closer to pi over 4, because that's going to get closer because of the ratio we have, the area of the circle to 4. Now here's the fun part, is that I can animate this, but let's go ahead and, so let's go ahead and start this up. So your code here, it's always a bit of a pain, and I always have to look up how to do some parts of this. So the first thing I need to do is set the world coordinates. So let's go up and look up how to do that. And this is no, I don't want to look up win.setWorld coordinates. Let's just go to turtle docs, right? What setting up world coordinates did, that's what your hurricane program did in the background to set it up so that X and Y were the longitude and latitude, okay? Set world coordinates over here, right? Okay, I can just do turtle dot set world coordinates, and it wants the lower left corner's coordinates and the upper right corner's coordinates, right? It wants to know, hey, your screen, what is this over here, and what is this over here? What are those coordinates on the coordinate plane? If you're defining your own custom coordinate plane, which I am. So I am going to say, hey, turtle dot set world coordinates. And that lower left, this is very easy. Lower left is -1, -1. Lower x, lower left x, lower left y, upper right x, upper right y. Right, and we're going to test this out. We're not going to take my word for it, because we always want to make sure when we're doing code we're unfamiliar with, we're going to make sure. Let's go ahead and make sure that Bob, we're going to just get our good friend Bob. Bob is equal to turtle.turtle. Bob.shape. And I'm going to make him a turtle. All right. And I'm going to tell him Bob dot go to 1, 1, or rather 1, 0. We'll go 1, 1. Doesn't matter where he goes to. The point being is that when I do this, we see that he ends up that the square we're in is now appropriately scaled, right? Let's go ahead and do 0.5 M1, right? It's appropriately scaled to the square. So we've created our square that we're bounding him in, okay? All right, next. We need him to start moving to random places. Import random, right? And now let's just get him to move to a random place, okay? X is equal to random.rand, and it's not rand int, right? I typically, in almost every program I'm going to give you, it's going to be rand. It's going to be like rand int, right? But for random, for a float, let's see, is not rand range. I think it's rand uniform or something weird. Like, yep, rand uniform. Rand uniform, such it's a random floating point number in between those two floating point numbers. Okay? If in that case, if you have to deal with that kind of thing on an exam, I'll give you that. I only expect you to know rand int and shuffle, right? That's what all I expect you to know for the exam. I expect you to be able to use Google and your brain to look up anything else like I just did. And the reason I look it up is because this terminology is different for every programming language. It's slightly different, right? I want to have to remember, wait, is rand int or rand bytes, is that capitalized or not? No, I'm going to look it up. Random dot uniform, -1, -1. Going to copy and paste that value. Copy, paste. Whoops, paste. There. Oh, no, -1, -1. That would just give me one. Right. We want the range to be from 1 to 1. Uniform meaning basically I want every point in that range to be considered to have an equal chance of showing up. And now what we're going to do is we're going to just simply say, Bob, hey, Bob, go to XY. I'll eventually just copy and paste this into a loop. Okay? But let's just go ahead and see this. I'm just going to hit. We can see now that he's moving randomly all over the place, but he's moving inside the bounds of the square, right? Okay. Cool. Let's go ahead and do a bit more setup. Bob dot up. We want him to raise his pen. So that way now I'm going to put this in a for loop. For blank in range, and we got to do this as I was doing it earlier, right? Trials is equal to, I'm just going to do 100 for right now because of the animation. Boop. And I don't even need to copy and paste it in. I'm just going to, whoops, tab that. And now I'm going to hit run. And now we can see that he's moving all over the place, right? We can see that he just moves to 100 different locations. He's actually doing that pretty darn fast. Bob.speed 2, right? We can see that he's going to... Oh, if you just tell him to go to without drawing, he just ups and goes. Wow, okay. So he's going to different places. That's cool. So let's go ahead and figure out whether or not we've got a, let's go ahead and figure out whether we've got a hit or not, right? Okay. So let's figure out whether or not we've got, so now we've got him, Bob is going to act as our dart, so Bob has graciously volunteered to be thrown at a dartboard a whole lot of times. So let's figure out whether or not he actually hits. So we're going to count hits is equal to 0. So we generate an x value and a y value. So our distance formula tells us whether or not it's a hit or not. Okay, how do we do distance again? Distance was, I'm going to say our distance is d, and I'm going to have to import math in order to use this. One kind of thing that I need to do for math. It's just one thing that's not that we just don't have intuitive ability to do, which is math.sqrt, which is not squirt, but math.square root, right? I always find it interesting because of where the vowels end up, but it is math.square root, and you just give it values, right? Because I just can't draw that function. Okay. And now we just need to do x squared plus, whoops, that's not plus y squared. There we go. And run. Okay? Of course, now it would help if I actually did something with that. So we can tell if it's a hit if d is less than or equal to 1. Then hits plus equals 1. And then print hits divided by trials, and that's supposed to approximate pi over 4, but I don't know what pi over 4 is off the top of my head, so I'm going to do hits divided by trials in order to do 4 times that, right? If it's pi over 4, then we did the same trick we did for the Madhav of Leibniz, which is we multiply our answer by 4 because our answer is supposed to be pi over 4. Multiplied by that 4, we're going to get something closer to pi. Right? So we run it, and we get 0.8 or 3.2. And this kind of makes sense because we've got 2 digits here, which is about as much as I expect with 100 trials. All right. We can, and then the comment suggested doing bob.tracer in order to get him to go faster. So let's do that. Bob.tracer. And that did go a lot faster, right? We can see that. I'm going to go ahead and share this code again. I'm going to share this code multiple times. I'm not close to done yet. Okay? But we see now that basically he's going all over the place. But now let's go ahead and actually mark our hits. Okay? Let's go ahead and mark our hits. Let's go ahead and actually show whether or not we hit something. Okay? So we know that we know from what we just did, if D is less than 1, or you're going to want less than or equal to 1, that's a hit. So we're going to signify that by saying bob.color. I'm going to say that's blue. If we want to show that Bob is hitting, we're setting the color equal to blue. And then otherwise, if we miss, I'm going to add an else here, and it's not going to increment hits, obviously, if it's not a hit. I don't need to keep track of the misses. So I've got red and blue. And so now, this will show up a bit interestingly. Again, I'll keep sharing my code as I go step by step. We see flickers now of it going, we've got red hits and we've got blue hits. Right? Red misses and blue hits. Share again. Finally, let's actually mark where we are going, right? Where the hits are. We're going to leave our darts in, so to speak. We're going to do that very simply by doing a stamp by each time we tell Bob to move, we're going to tell him then to stamp. Bob.stamp. Okay, save and run. Actually, let's go ahead. And we start to get something interesting. So there's our hits, there's our misses. Let's actually up the number of misses, the number of trials to 1,000. And now, it turns out we're drawing a circle. From all the hits we're making and all the misses we are missing. And that does, okay, interesting. Hits divided by trials gives me 7.92. And 3, why is that 3.1? Shouldn't it be pi over 4? What am I calculating wrong here? Because the circle's coming up correctly. Hits divided by trials. Oh, that's why. Silly me. That's why I have trials to begin with, so I only have to change a single variable in one place. There we go. Sorry for keeping it so small. Let me go ahead and share it again. Okay. And now we see that we've got an approximation of 3.2. Let's look up what tracer does so that we can bump these rookie numbers higher, okay? Okay, so Control F, tracer gives us a none, and if n is given, only each nth regular screen update is performed. Delay value, see delay, which is set the drawing delay in milliseconds. Okay? So can I turn that down to like 5 and then draw really fast? Because I don't care how fast it goes to draw. Just care that it gets drawn. Or what if I do what if I do a second delay for drawing? Yeah, it's going to go forever. Yeah, we don't want that to be anywhere near this high, so we got to wait for it to time out, which is 30 seconds. Yeah, okay. There we go. Good. Timed out. So let's go ahead and shrink that down to like... Okay. Let's go ahead and get this back down to a reasonable value. Let's draw only every 30 frames, and we'll take a 5 millisecond delay between them. And that goes much quicker because we are not drawing every single motion the turtle's making. Let's go ahead and bump up now the trials to 10,000. You can easily make this run 10 times as long. Boom. And that's pretty cool. And we can see from our formulas that we were doing, now that we've got 10,000 going, we can see that we get more digits of pi closer to correct. 3.13 as opposed to 3.14. So we can use Monte Carlo. So this is, again, even though it doesn't seem like it, it is Monte Carlo. All right. Now, let's see. We have 20 minutes left, so let's take a look at the practice exam for just a minute. And then I'm not going to go over any of the problems because I'm not going to solve any of the problems because I want to give you the chance to work on it independently as you are as you're studying. So, again, if you want to find out where your practice exam is, it was in the announcements. Announcements over here. I shouldn't I? Yes. Share. I'm going to share it one more time. There we go. Okay. Now, going over here to our practice exam. Okay. Again, much longer and more difficult. A lot of these points over here are 0 points because there's not actually anything like them on the actual exam over here. These original ones. These are, like I said, these kind of questions won't be on the exam. They used to be. But these are good review questions to kind of just remember what our concepts are. And they're kind of important for succeeding on the exam. They're good review questions just to kind of warm up on. As I mentioned a couple times, this is an actual question from the previous exam where you're given a file and you're asked to go over basically you're asked to find the highest highs and the lowest lows. Other comparable questions, for instance, on the final exam, I've asked for the file reading question on the final exam, I've asked, hey, here are the various characters in a game of Mario Kart. Here's the time at which they finished, who won, right? In other words, who had the lowest time. So fairly straightforward kind of things. But they all revolve on that skill that you learned, those skills you learned in your Hurricane Lab, which is opening the file, and you don't have to worry about it being in a separate folder. You're just given the name of the file. So opening the file, reading it line by line, and then splitting that line in order to get the individual data fields, right? And once you're getting the individual data fields, you can then do something with them. It's not going to be particularly complex, right? Over here, it's basically saying, hey, keeping track of what is the largest thing. That's what you're doing. Keeping track of what's the largest one of these and the smallest number of these. Okay? similar question, but also completely different, is here's a bunch of numbers separated by commas, but give me the sum of all the even numbers. The vast majority of the exam will be problems like this. Here's a function. And for every single function, I'm going to give you a bunch of stuff. First thing I'm going to give you is obviously the problem definition, right? Un or un. This one says if a word begins with un, remove the un from it. If it does not begin with un, add un in front of it, right? This one's, okay? For each of these problems, I don't have this on the practice exam, but you will get a rubric, which will work for every single problem, and that will act as kind of a, oh God, what am I supposed to do? Look at the rubric. It's kind of a hint as to what steps you should take, okay? But it will also give you input-output pairs, basically saying, hey, here's an example. If I were to put your thing in the computer and remove like and fix some of the very minor mistakes you made, like forgetting a colon or something, these are what I'd expect to get, right? Un or un, right? Untied goes to tied, unable goes to able, necessary goes to unnecessary. Min-max difference, given a list, find the difference between the biggest number and the smallest number. Some of these I grabbed from Coding Bat because they're really good. This one's a fun one. Given an integer, return the sum of the digits of 0 to 9 of that integer. This one's important because remember, you can't just do a for loop over an integer. You can't say 4-digit in number, add the digit up. You have to do something with it. You either have to use a while loop and use modular arithmetic and division to solve that one, or you can be completely lame but very efficient and then convert it into a string and then convert each letter of the string back into a number, which is totally lame and totally works. Either way, because on these exams, I don't care so long as it works. Yes?
How come you can't use for loops? Shouldn't
You can't use a for loop on a non-iterable, right? An int isn't iterable. You're thinking a for I in range number, but that goes from 0 up to this number. I'm asking for the sum of its digits. Here, the sum of these digits are 1 plus 2 plus 3 plus 4. The sum of these digits are 1,000. Try it. It's not going to work. You got to be creative with your solution there. Right? So, Monte Carlo problem. So, with dictionaries, I'm pretty much telling you in advance what the problem is going to be. Okay? We're given a string, write a function that returns the most common letter in the string. Use the dictionary to do this. Or, given a string, return the most common word in the string, right? Words are separated by spaces. Ignore punctuation, right? Or you can assume there is no punctuation, right? Given us, something like that. Given a list of words, give what is the most common word, right? Those kind of things, right? But for the dictionary problem, I'm saying, given X, find the most common Y, okay? Or given a collection of X, find the most common thing in that collection. This is going to be slightly harder than what I would give you on the exam in terms of complexity of the problem. Okay? Which is, it's a coin tossing problem, which in itself is fairly straightforward. Tossing a coin, basically you create a heads or tail, a dice or a list with H and T in it, and you just generate which one do you want. This one's pretty interesting. But it is a good program for, this is definitely harder than I would put on the actual exam. The problem itself isn't harder, the rules are a bit more complex than what I would put on the exam, even though it's just this. Okay? But these kind of problems are very good. The only other kind of suggestion I have for practicing for the exam is working on the extra credit pig problem. Okay, so let me go over what pig is, just to kind of, because it's available as extra credit for y'all. Okay, it's typically the homework you'd be working on right now, but I wanted to make sure that things got slightly less crazy this semester. So it's been moved to extra credit. Pig is a game of chicken, which I find hilarious that I'm using an animal name to describe another animal name, right? Pig is a game of chicken. A chicken being basically these kind of games that who's gonna blink first, who's gonna stop first, okay? Pig, basically the rules are very simple. You want to be the first player who gets to 100 points. Okay, on your turn, it's your turn with the 6-sided dice, and you get two choices on your turn. You get two choices. You can roll the dice and you can roll the dice to gamble on receiving points, or you can end your turn and bank all the points you've made for the turn safely. Okay, when you roll the dice, if you roll a 2 or higher, you get that many points, or you earn this many. You earn this many points. Except if you roll 1, right, 6-sided die. So if you roll 1, you lose all the points you've made this turn. You keep all the points you've previously banked, but everything you've made this turn you lose. So basically you roll, you get a 6. Do you want to try again? I'm going to roll, I get a 4. It's 10 points so far. I'm going to decide to bank. My opponent rolls a 3, a 5, a 6, and then a 1. So gets nothing, and it's now my turn, because his turn ends when he rolls a 1. Now it's my turn again, right? I roll a 6, and then another 6. I've got 22 points now. I've got 12 points now. I'm going to bank for a total of 22. Now my opponent has to make a choice. Is he going to play more aggressively to try to catch up, or is he going to try to play conservatively to not remain at 0? Okay? And this is an 8-part problem, which I will slowly go over, right? But the idea here is that we build up the entire game from scratch while doing some analysis on it, right? And asking some questions. What you do as part of this is kind of program a strategy for the computer, which is that the computer gets the strategy of earning 20 points a turn. Okay, the computer strategy is I'm going to roll until I have at least 20 points. Once I hit 20 points, I'm going to stop. Okay, and this is important because I have to make a lot of people correct this. And now the more I think about it, the more I think about it possibly being an issue with the AI misunderstanding for students who do this, because I have to correct a lot of students about this. The player, a human player, right? The computer strategy is I'm going to earn 20 points. The human's allowed to do whatever the heck they want. They can try to go for broke. In fact, if you do the statistical analysis of it, you'll find that going for broke, in other words, rolling the die on your turn until you hit 100 points, actually works 1% of the time. So, like, if I had everybody in the class do it, I would not be surprised if somebody ended up doing it, managing to get 100 points without rolling a single one. It's possible. It is possible. But it's a very low. It's not a very safe strategy. So but humans are allowed to be as dumb as possible. So that's the main thing. But it's basically broken up into 8 parts. Where we're just simply making the computer do a single turn, then basically figuring out what are the possible outcomes of that, and then making that strategy adjustable. Making that strategy adjustable to be, rather than being, hey, I want to just be 20 points, maybe I want to be 10, be 30, see how many points I can get. So you can see that this is pretty good for, and the way you do this is you use dictionaries. And when you're doing simulations like this to figure out the estimated probability, that's doing a Monte Carlo approximation. So this is very kind of good practice on those kind of problems. Okay? If you are looking for more and more kind of challenges and need more practice, First off, coding bat in general is pretty good at your level, and I've mentioned this one before. It has Python problems here. But if you're really chomping at the bit to really try some interesting stuff, my personal preference is Project Euler, which is a lot of math-focused problems. Like a lot of math-focused problems that require computers to solve. Some of them require interesting mathematical knowledge, although some of them are like stuff we discussed in class today, like the Collatz conjecture, right? What starting number under 1,000,000 produces the longest Collatz chain? This one's fun. Starting at the top left corner of a 2x2 grid and only being able to move right and down, there's exactly 6 routes to the bottom right corner. How many such routes exist in a 20x20 grid? And that's that one. Some of these also might seem really easy, and am wondering why that's even a problem. For instance, you might work out the first 10 digits of the sum of the following 150-digit numbers, right? So you have to add up all these numbers and figure out what the first 10 digits are. Figuring out the first 10 digits really isn't that hard, especially if you decide to convert it into a string after you've added them all up, right? But adding these numbers up, if you're doing that in Python, you might actually be wondering what the heck the problem is. And the answer is, it's not a problem in Python. It's a problem in other programming languages, because these are numbers than the other program. These numbers are bigger than what other programming languages allow for integers and longs, which are bigger integers. So you have to figure out how your programming language gets around that problem. So these are a lot of fun kind of mathematical problems. I've done quite a number of them. And there's a bunch that I haven't done. Some of them require some interesting problems. Let's see, and some of them do require file reading. Let's see. Some of them I give as like this one. For passcode derivation, that's one I give as an assignment in one of my other classes. Maximum path sum. Given a file, this file, figure out the largest path through this file. That's a good one. Poker hands. Right? What is the problem? How many hands does player 1 win? Interesting. Okay. And then finally, since we're getting close to the holiday season, okay, just as a warning that since we're getting close to the holiday season, this won't start until much later, but there is a yearly thing that has started, and there's an entire subreddit dedicated to it. I know, I'm breaking multiple taboos by bringing up Christmas stuff, and it's not even Halloween yet, but it's worth knowing about this, that it is coming up. Advent of Code. Also starting this year, there'll be only 12 days of puzzles. Makes sense, okay? I suppose, because it was hard. Yeah. 10 years, yeah, he's been doing this. So, previous years, he's done, let's see, so basically these are a bunch of kind of Christmas-themed programming problems. Basically, Santa's having an issue, and only you, the programmer, can save Christmas, essentially, kind of things. And doing the problems gives you helps you create a Christmas tree. So, so what floor do the instructions take Santa? And so these are very fun themed problems, and they're good practice. And also, like I mentioned, there's an entire subreddit dedicated to these things, so you can totally get help, and it's just, I would find things that appeal to you. Mathematical puzzles appeal to me because I'm weird, okay? But some other game-themed stuff might appeal to other people. At the end of the day, the only way you really get better at programming is by practicing, okay? And so you might as well practice on something you enjoy, okay? Hence why we're doing this entire entire final project. All right, with that, you're all dismissed. Do your best to stay dry, although I think the majority of rain falling from the sky is over. And now we just have to deal with our puddles.